So, what if you could build a single computer that was powerful enough to monitor the entire planet? I mean, a tool that lets us see the health of every single forest, every river, every city, all at once. Well, today, we're going to look at a technology that does pretty much exactly that. And you know what? It is changing everything.
I mean, just stop and think about that for a second. How would you actually do that? How do you take the pulse of an entire world in near real time? Every forest, every ocean, every single city. The scale of that is just mind-boggling. Well, the core challenge is something scientists call geo-big data. You see, every single day, our satellites and sensors are beaming down this absolute fire hose of information. We're talking about its sheer volume, we're talking petabytes of data. Then there's its variety, everything from what looks like a normal photo to complex radar scans. And of course, its velocity, the incredible speed that all this new data is arriving. It is a flood of information so massive that your standard computer just can't keep up. So how do you even begin to solve a problem that big? Well, you build a bigger tool, and that tool is Google Earth Engine. Just imagine taking all of that planetary data and plugging it into one giant cloud-based computer that anyone can use to ask really, really big questions. That's essentially what this platform does. But to really get a feel for it, let's dive into a specific example. Okay, let's make this super real with a question that sounds simple but is actually incredibly profound. How do you weigh a forest? Not just, a single tree, but an entire ecosystem from space. And you're probably thinking, why on earth would you even want to do that? Well, the answer turns out to be absolutely critical for understanding our changing climate. You see, forests act kind of like the planet's lungs. They breathe in CO2 and they store that carbon in their wood, their leaves, their roots. Scientists have a name for this total weight of organic matter, above ground biomass, or AGB for short. Put simply, it's a direct measure of how much carbon a forest is holding on to. The problem has always been how to measure it. The old way, you'd literally have to go cut down trees and weigh them, which is slow, it's destructive, and it's completely impossible to do on a global scale. So, researchers turned to remote sensing. This study, right here, it focused on the beautiful temperate forests of Adirondack Park in New York. And the goal was simple: use satellite data processed in Google Earth Engine to weigh the forest from space and figure out the absolute most accurate way to do it. And this led them to a fascinating head-to-head comparison between two totally different ways of seeing that forest. Should they analyze it pixel by pixel, or should they group those pixels into meaningful objects first? Okay, so the traditional pixel-based method looks at a satellite image one tiny square at a time. A great way to think about it is like trying to understand a pointillist painting by staring at each individual dot one by one. The other method, object-based analysis, is a lot smarter. It first groups similar pixels together into meaningful shapes, like a whole stand of trees or a clearing. Then it analyzes those objects. It's like stepping back from the painting to actually see the picture. Now, to do this, they used a really powerful combo of data. First, optical satellite imagery, which is basically a giant digital camera in space. But they also used something called SAR, or synthetic aperture radar. Think of SAR like a bat's sonar. It sends out a radar pulse, and then it measures the echo that bounces back. This lets it map the physical structure of the forest, the trunks, the branches, and it can even see right through clouds. The big bet was that combining both of these, the optical and the radar, would create the most accurate picture possible. So they ran the models, they compared the different methods, they crunched all the numbers inside Google Earth Engine. So which one came out on top? Was it the classic pixel-by-pixel approach, or was it the smarter object-based view? The results were crystal clear. This chart here shows the error rate, and all you really need to know is that lower bars are better. The striped bars? That's the old pixel method. The dotted bars are the new object-based method, and as you can see in every single test, the dotted bar is lower. The object-based method was consistently more accurate. It gave them a much more reliable weight for the forest. So just how much better was it? Well, in some cases, seeing the forest as objects instead of just a bunch of pixels reduced the estimation error by over 22%. Now that is a massive leap in accuracy. It's a huge deal when you're trying to balance the entire planet's carbon budget. So the key takeaways here are really clear. First, grouping pixels into objects is way more accurate. It actually helps solve what's called the mixed pixel problem, where one pixel on the edge of a forest might have both trees and bare ground in it, which confuses the analysis. Second, the data confirmed it. The best results always came from combining what we can see with optical light with what we can measure with SAR's structural data. That combination gives us the most complete picture. Okay, so let's zoom back out, because weighing one forest in New York, as cool as that is just the beginning. The real power of this planetary computer is what it lets us do everywhere else. This very same technology is being used to tackle an absolutely incredible range of global challenges. Scientists are using it to estimate crop yields to help with food security, they're mapping floods and droughts in real time, they're tracking how our cities expand, and they're monitoring the health of our vital wetlands. And this isn't some niche tool for a handful of scientists. This is a global phenomenon. Peer-reviewed studies using Google Earth Engine have already happened in over 104 different countries, covering every single continent on Earth. As the authors of a major review paper put it, the platform is making substantive progress on global challenges. What that really means is that it's democratizing access to planetary data. It's allowing more scientists in more places to help protect our world. And that leaves us with a final and pretty crucial question. For the first time in history, we can actually see and analyze our entire planet as one big, interconnected system. So now that we have this unbelievable, unprecedented power, what will we choose to